Hello and welcome to General Astronomy Lecture 29, Neutron Stars and Black Holes. Welcome to the afterworld of stars, the fascinating domain of white dwarfs, neutron stars, and black holes. Note that we've discussed white dwarfs previously in Lecture 27. To scientists, these dead stars are ideal laboratories for testing the most extreme predictions of both general relativity and quantum theory. To most other people, however, the eccentric behavior of stellar corpses demonstrates the universe is far stranger than ever imagined. Dead stars behave in unusual and in unexpected ways that challenge our minds and stretch the boundaries of what we believe is possible. Stars that have finished nuclear fusion have only one hope of staving off this crushing power of gravity, the quantum mechanical effect known as degeneracy pressure. But even the strange pressure cannot save the most massive star cores. In this video, we will study the bizarre properties and occasional catastrophic events of these eerie inhabitants of the stellar graveyard. A supernova remnant may be all that is left after some supernova explode, but for core collapse supernovas of type 2, 1b, and 1c, the core itself may also remain. If there is a relic of the core, it may be either a neutron star or black hole, depending on the mass of the core and the conditions within it during its collapse. Neutron stars, as the name suggests, are made primarily of neutrons. Note again that we did discuss these other items such as white dwarfs, red dwarfs, and brown dwarfs in past videos. But I love this image here. It's basically just a guideline to let you know how stars will end their lives based on their masses. So in this video, we're going to focus on neutron stars and black holes. Neutron stars are the relics of stars that have an original mass of 8 to 25 solar masses, and anything beyond about 25 solar masses will become a black hole. So let's start with neutron stars. On the morning of July 4th, year 10,054, Yang Vi, the imperial astronomer to the Chinese court, made a startling discovery. Just a few minutes before sunrise, a new and dazzling object ascended above the eastern horizon. This, quote, guest star, as Yang called it, was far brighter than Venus and more resplendent than any other star he had seen. Yang's records show that this, quote, guest star was so brilliant that it could easily be seen during broad daylight for the rest of July. Records from Constantinople are also describing this object, and works of art in the American Southwest suggest that people there may have seen it as well. This drawing is an 11th century structure in New Mexico that shows a 10-pointed star next to a crescent, as you can see on the image here on the right. It may depict the scene on the morning of July 5th, 1054, when the guest star appeared next to a waning crescent moon. Over the next 21 months, however, the guest star faded into invisibility. We now know that the guest star of 1054 was actually a remarkable stellar transformation. A massive star, some 6,500 light-years away, perished in a supernova explosion, leaving behind both a supernova remnant and a bizarre object called a neutron star. Recall that during the collapse of a massive star, the core becomes so dense that the negatively charged electrons within it are forced to combine with the positively charged protons to produce what we call neutrons and neutrinos. You can see the reaction at the end of the first paragraph here. Far from being a rare transformation, a core collapse can convert over a solar mass of material into pure neutrons. A neutron star is the ball of neutrons supported by neutron degeneracy pressure created by the collapse of an iron core in a massive supernova explosion. Recall that white dwarfs are supported by degenerate electron pressure, and by a similar effect, neutron stars are supported against further gravitational collapse by this degenerate neutron pressure. So what are some properties of neutron stars? These are one of the most amazing objects in the universe. Well, we remember that white dwarfs with densities of several tons per teaspoon may seem incredible, but neutron stars are stranger still. The possibility that neutron stars might exist was first proposed in the 1930s by many astronomers thought it preposterous that nature could make anything so bizarre. Nevertheless, a vast amount of evidence now makes it clear that they really do exist. So first up, neutron stars are typically just 10 to 20 kilometers or 6 to 12 miles in radius, but yet happen to be more massive than the Sun. Neutron stars can only exist for a narrow range of masses, supported by degenerate electron pressure. Stellar cores below the Chandrasekhar limit of 1.4 solar masses form white dwarfs. Above this limit, however, neutron stars form. The maximum possible mass of a neutron star is only about 2 to 3 solar masses. Beyond that, a stellar core will create a black hole. These objects are so dense that if brought to the Earth's surface, a single teaspoon of neutron star matter would weigh nearly 100 million tons, or as a comparison, you could say about 20 million elephants. The gravitational field at the neutron star's surface is that about 200 billion times that of the Earth. That's 2 times 10 raised to the 11th power. Its surface gravity would be so strong that its escape speed, that is, the speed an object would need to have to leave the surface, would be 1/2 the speed of light. Even climbing a 1 millimeter step on a neutron star would require about the same energy as a person jumping straight to the moon from the Earth. If an object were to fall from a height of 1 meter on a neutron star, so maybe you're holding a penny, let's say, 1 meter off the surface, and you drop it, it would reach the ground at about 1,400 kilometers per second, or 3 million miles per hour. However, even before this impact, the tidal forces would cause what we call spaghettification, breaking any sort of ordinary object into a stream of material. If you foolishly choose to visit a neutron star's surface, you would be squashed immediately into a microscopically thin puddle of subatomic particles. There are thought to be around 100 million neutron stars in the Milky Way galaxy alone, a figure obtained by estimating the number of stars that have undergone supernova explosions. Before we move on, let's just tell a quick story. A paperclip with the density of neutron star material would outweigh even Mount Everest. If such a paperclip magically appeared in your hand, you could not only prevent it from falling, but it would downright plunge, passing through the Earth like a rock falling through air. It would gain speed until it reaches the Earth's center, and its momentum would carry it onward until it slowed to a stop on the other side of the planet. Then it would fall back down again. If it came from space, each plunge of the neutron star material would drill a different hole through the rotating Earth. In the words of astronomer Carl Sagan, the inside of the Earth would look briefly like Swiss cheese. That is, of course, until the melted rock flowed to fill in these holes. By the time friction finally brought the piece to rest, that's what we would see. In the unfortunate event that an entire neutron star came to visit you, it would not fall at all. Because it would only be about 10 kilometers in radius, the neutron star would probably fit in your hometown. Remember, however, that it would be 300,000 times as massive as Earth. As a result, the neutron star's immense surface gravity would quickly destroy your hometown and the rest of the planet. By the time the dust settled, the former Earth would be squashed into a shell no thicker than your thumb on the surface of the neutron star. So, just a few happy thoughts before we move on. The first observational evidence for neutron stars came in 1967, when a 24-year-old graduate student named Jocelyn Bell discovered a strange source of radio waves. Bell had helped her advisor, Anthony Hewish, build a radio telescope ideal for discovering fluctuating sources of radio waves like she was seeing. She was busily trying to intercept the flood of data pouring out of the instrument in October 1967 when she noticed a peculiar signal. After ruling out other possibilities, she concluded that pulses of radio waves were arriving from somewhere near the direction of the constellation Cygnus at intervals of precisely 1.337301 seconds. The pulses coming from Cygnus were very surprising because no known astronomical object pulsated so regularly. In fact, the pulsations came at such precise intervals that they were nearly as reliable for measuring time as the most precise human-made clocks. Furthermore, they were so rapid and regular that the Cambridge team first wondered that they might be signals from an advanced civilization. Today, we refer to such rapidly pulsating radio sources as pulsars. Pulsars are rapidly rotating neutron stars from which we see pulses of radio wave radiation. The periods of these pulsars are extremely regular, ranging anywhere from about 0.001 second for the fastest to about 8 seconds for the slowest. Because neutron stars are very small, they should also rotate rapidly. A typical star, such as our Sun, takes nearly a full month to rotate once around its axis. But just as a spinning ice skater speeds up when she pulls in her arms, as a star's core collapses, its rotation rate also increases as a result of the physical property known as angular momentum. Hence, newly formed neutron stars will rotate at up to several hundred times per second. To give an example, if our Sun were compressed to the size of a neutron star, it would spin about 1,000 times per second. Because neutron stars are so small and dense, they can spin this rapidly without flying apart. The fastest spinning star known is called PSR J1748-2446 AD. Didn't come up with that one, but it's a heck of a name. It rotates at a rate of 716 times every single second, or 43,000 revolutions per minute, giving it a linear speed at the surface on the order of a quarter the speed of light. In other words, if you were to stand on its surface, you'd be traveling at about a quarter the speed of light simply by being on such a fast rotating object. So why are they getting pulses of radiation coming from these objects? Well, in addition to the increasing rate of rotation, collapse of a stellar core also bunches the magnetic field lines running through the core far more tightly, greatly amplifying the strength of the magnetic field. The magnetic field of a main sequence star is spread out over billions of square kilometers along the star's surface, like our Sun. However, if such a star collapses down into a neutron star, its surface area shrinks by a factor of about 10 billion. Shortly after its formation in a supernova, a neutron star's magnetic field is 1 trillion times as strong as Earth's. The magnetic field of a neutron star makes it possible for the star to radiate pulses of energy toward our telescopes. As a neutron star rotates, the magnetic axis of the neutron star, that is, the imaginary line passing through the north and south magnetic poles, as you can see in the image on the right, is likely to be inclined at an angle to the rotational axis of the object. So you can see here the axis of rotation, so the object is rotating along an axis pointing straight up and down. But the north and south pole are tilted away from that just a little bit. So in other words, you're going to see this beam of radiation sweep out circles following this orange arrow here. And whenever that passes us, we will see radiation. So, furthermore, nearby electrically charged particles are accelerated along this magnetic field, and this motion produces electromagnetic radiation. The result is that two narrow beams of radiation pour out of the neutron star's north and south magnetic poles. Like lighthouses, neutron stars actually emit a fairly steady beam of light, but we see this as a pulse of light each time the beam sweeps across Earth's point of view. The continual twirling of a pulsar's magnetic field generates electromagnetic radiation that carries away energy and angular momentum. The neutron star's rotation rate slows gradually as a result. The pulsar in the Crab Nebula, for example, currently spins at about 30 times per second, but 2,000 years from now it will spin less than half as fast. Eventually, a pulsar's spin slows so much and its magnetic field becomes so weak that we can no longer detect it. In addition, some spinning neutron stars may be oriented so that their beams do not sweep past our location. Well, beyond 2 to 3 solar masses, not even neutron degeneracy pressure is strong enough to resist the crush of gravity. If a stellar core exceeds this mass, it will collapse into a black hole. To understand black holes, we must first grasp the nature of space and time as described by Einstein's special theory of relativity. The special theory of relativity is a description of mechanics and electromagnetic theory formulated by Albert Einstein, which explains the measurements of distance, time, and mass as they are affected by observers' motion. In particular, the distance between 2 points is not an absolute, nor is the time interval between 2 events. Instead, the values that you measure for these quantities depend on how you are moving, and these values are relative to the observer. Remarkably, Einstein's theory is based on just 2 principles. 1. Your description of physical reality is the same regardless of the constant velocity at which you move. And 2. regardless of your speed or direction of motion, you will always measure the speed of light to be the same. It doesn't matter how fast you're moving, you'll always measure the speed of light to be the 3 times 10 to the 8 meters per second we've come to know. In other words, by the first principle, if you are moving in a straight line and at a constant speed, you experience the same laws of physics as you would if you were moving at any other constant speed in any other direction. The first principle is what we experience in everyday life, when riding on a bus or flying on an airplane. Phenomena inside the flying airplane, such as dropping a book, appear to be the same as if when the plane was on the ground, even though you were moving. And this would still be true if the plane could fly near the speed of light. To see what the second implies, imagine that you are in a spaceship that is moving toward a flashlight. Even if you are moving at 99% the speed of light, you will measure the photons of light coming from the flashlight to be moving at the same speed, as if your spaceship were motionless. So, this is where it starts to get really, really interesting and incredible. One of the peculiar aspects of Einstein's theory of special relativity is that the length you measure an object to be depends on how the object is moving. The faster the object moves, the shorter its length along its direction of motion. This is known as length contraction. In other words, if a railroad car moves past you at a high speed, from your perspective on the ground, you will actually measure it to be shorter than if it was at rest. However, if you are on board the railroad car and you're moving with it, you will measure its length to be the same as measured on the ground when it was at rest. So the person outside sees the train being shorter if it's moving very quickly, but if you were on the train, it wouldn't seem any shorter. That's why the word relative comes into play. The word relativity emphasizes the importance of the relative speed between the observer at rest and the object being measured. If the idea of length contraction seems outrageous, it is because this effect is noticeable only at very high speeds near the speed of light. But even the fastest spacecraft ever built by humans traveled at a mere 1 over 25,000ths the speed of light. At this speed, a spacecraft 10 meters long would only be contracted by about 8 nanometers, the distance equal to the width of a single protein molecule. So not even our fastest spacecraft made yet will have any real noticeable effect. So it's not super important in our everyday lives. Well, even more interestingly, the time that you measure a clock to have also depends on how the clock is moving. Again, the faster it moves, we see a different reaction. If a clock is moving at a high speed, it will see time progress more slowly. This is known as time dilation. Like length contraction, this time dilation is a very small effect unless the clock is moving at extremely high speeds. Nonetheless, physicists have confirmed the existence of time dilation by using an extremely accurate atomic clock carried by a jet airliner. When the airliner landed, they found that the onboard clock had actually ticked off slightly less time than an identical stationary clock on the ground. For the passengers on board the airliner during this experiment, however, time flowed at a normal rate. The onboard clock ticked off the seconds as usual, their heartbeats at a normal rate, and so on. You only measure a clock or, say, a beating heart to be running slow if it is moving relative to you. For a closer look at the special theory of relativity, I really highly recommend watching a brief video on the subject from Crash Course Physics before moving on. So I would stop the video here and take a look at it. I included a link in the description. Now, this is actually a really interesting result because when I was in school, I actually had a professor who was an astronaut, and he often bragged about the fact that he is younger because he was up in space moving at high speeds than he would be if he didn't do any of this. Now, it was only about, if I remember correctly, 6 or 8 microseconds that he's younger because he did it, but he's very proud of that time. Well, Einstein's special theory of relativity is a special case in the sense that it does not include the effects of gravity. Einstein's next goal was to develop an even more comprehensive theory that includes gravity and its effects on the space and time that we exist in. This is Einstein's general theory of relativity, which he published in 1915. In the special theory of relativity, relative velocity between observers leads to different observations of distance and time, as we discussed in the previous slide. In addition to all of the effects of the special theory, the general theory of relativity describes how observers in gravitational fields of different strengths also measure differences in distance and time. General relativity has been described as the most beautiful of all existing physical theories. Einstein envisioned gravity as being caused by the curvature of space. In fact, his general theory of relativity describes gravity entirely in terms of the geometry of both space and time. That is what we call space-time. It is a four-dimensional combination of time and the three-dimensional regions of space. So, in this case, we aren't perceiving gravity as a force. We're perceiving it as an effect caused by warping of space. Now, this sounds crazy, but bear with me. Far from a source of gravity, like a planet or a star, space-time is flat, as you can kind of see in the distance of the image on the right. And clocks tick at their normal rates. However, closer to a source of gravity, space is curved and clocks slow down. So take a look at the image on the right and we'll try to make a comparison. A useful analogy is to picture that space-time near a massive object such as the sun is being curved like the surface in the figure. Imagine a ball rolling along this surface. Far away from the well that we see, which represents the sun, the surface is fairly flat and the ball would move in a straight line. If the ball passes near the well, however, it curves toward it. If the ball is moving at an appropriate speed, it might move in an orbit around the sides of this well. The curvature of the well has the same effect on a ball of any size, which explains why gravity produces some acceleration on objects of different masses. For an incredible and straightforward physical example of how this fabric of space-time works, I really also recommend watching this, quote, gravity visualized video before moving on. It's a quick demo that this, I think he's a high school teacher, made, just using spandex and masses to warp space like you can see on this image here. It's a really, really good physical demonstration and I recommend it before moving on. Now, there are two unique consequences of general relativity that I wanted to bring up before we move on again. The first is what is known as gravitational lensing. If the space through which light rays travel is curved, as happens when light passes near the surface of a massive object like the sun, the paths of the rays will likewise be curved, just like a ball rolling on the well that we talked about in the previous slide. In other words, gravity actually bends light rays in a process known as gravitational lensing. This serves as one of many experiments that verify the key ideas of Einstein's theory of gravity. To draw a comparison, again, imagine placing a heavy bowling ball on your bed. The ball deforms the surface of your bed. Now take a marble and roll it straight toward the edge of one of the sides of the bowling ball. Rather than taking a straight path, we'll see that the marble will end up rolling toward the bowling ball. This is what happens to light near a massive object, as you see in the top right. Here is a star. Well, its light is coming out at a straight line, but as that light approaches a massive object, it gets bent. So our telescope, looking in this direction, thinks that the object is over here, where we observe it. But it's actually behind the white dwarf, and its light was simply bent around it. This sounds crazy, but we actually have visual evidence of this. And that's why I brought up this first image. Here you actually see a very massive galaxy in the center, and you see this weird ring around it. This is actually a galaxy behind the one that you see in the middle, but its light is being bent around the massive object, just like we see here. And here's a few more examples. In this image on the right, we can see lots of different gravitational lenses. You can see one around the massive galaxies here. You can see some bent images here and all around the edges. But my favorite image, probably in all of astronomy, is the middle one, a cosmic smiley face. Another consequence of general relativity is gravitational waves. This is becoming very important in today's climate. Gravitational waves are ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe. Einstein predicted the existence of these waves in 1916 in his theory of relativity. Einstein's mathematics showed that the massive accelerating objects such as neutron stars or black holes, when orbiting each other, would disrupt this space-time in such a way that waves would distort space and radiate away from the source, quite like the movement of waves radiating away from a stone that's thrown into a pond. Furthermore, these ripples would travel at the speed of light through the universe, carrying with them information about their cataclysmic origins as well as invaluable clues to the nature of gravity itself. On September 14th in 2015, LIGO, for the first time, physically sensed distortions in spacetime itself caused by the passing of gravitational waves. And in this case, they were created by two colliding black holes nearly 1.3 billion light-years away. LIGO and its discovery will go down in history as one of the greatest human scientific achievements. For a closer look at gravitational waves and their understanding, I highly recommend watching the video that I linked in the description from PhD Comics. Perhaps the most dramatic prediction of the general theory of relativity concerns what happens when a large amount of matter is concentrated in a small volume. We have seen that if a dying star is not too massive, it ends up as a white dwarf. If the dying star is more massive than the Chandrasekhar limit of about 1.4 solar masses, it cannot exist as a stable white dwarf and instead will shrink down into a neutron star. But if the dying star has more mass than the maximum permissible mass of a neutron star, about, say, 2 to 3 solar masses, not even the internal pressure of neutrons can hold the star up against its own gravity. The core will collapse without end, crushing itself out of existence and forming perhaps the most bizarre type of object in the universe, a black hole. As the star's core becomes compressed to enormous densities, the strength of gravity at the surface of this rapidly shrinking sphere is also increased dramatically. According to the general theory of relativity, the space immediately surrounding the object will become so highly curved that it actually closes in on itself. Photons, or light, flying outward at an angle from such an object's surface would actually arc back inward, while photons that fly straight outward would undergo such a strong gravitational redshift that they lose all of their energy and cease to exist. So I'm trying to show that in this image here. So if you have just a simple star, light is radiated out in all directions, as we would expect. As we see from our own sun, we see light coming from all directions. But note, as we get to more and more massive and dense objects, like a neutron star, that light is starting to get bent a little bit because the gravity is so strong around these objects. But if we get to a dense enough object, such as a black hole, light is not even quick enough to escape. It tries to leave, and then it gets bent back down toward the surface. And anywhere within this region, we see the black hole, or darkness. Ordinary matter can never travel as fast as light. Hence, if light cannot escape from the collapsing core, neither can anything else. An object from which neither light nor matter can escape is what we call a black hole. In a sense, it is a hole punched in the fabric of the universe, and the dying star disappears into this cavity. One way to understand black holes is to first consider the escape speed from a planet. The escape speed of a planet is the minimum ejection speed an object must have at the planet's surface in order to escape the planet and never return. Very importantly, if you imagine compressing a planet's mass into a smaller radius, the planet's escape speed will increase, meaning you have to travel at higher speeds to leave. It is even possible, if an object were compressed into a small enough radius, that its calculated escape speed would exceed the speed of light. Since nothing, not even light, can travel faster than that speed, nothing would escape such an unusual object. The boundary between the inside of a black hole and the universe outside, where the escape speed equals the speed of light, is what we call the event horizon. You can think of the event horizon as the, quote, surface of the black hole, although it is just a spherical boundary, not a physical one. Once a massive dying star collapses to within its event horizon, it disappears permanently from the universe. The term event horizon is quite appropriate because it is at this surface that looks like a horizon beyond which nothing can be seen. In other words, you can't see any events beyond it. We usually think of the size of a black hole as the radius of its event horizon. The radius of the event horizon is known as the Schwarzschild radius, named after Karl Schwarzschild, who lived from 1873 to 1916. Schwarzschild computed his famous radius from Einstein's general theory of relativity only a month after Einstein published the theory. Moreover, he did this work while serving in the German army on the Russian front during World War I. Sadly, he died less than a year later of an illness contracted during the war. The Schwarzschild radius of a black hole depends only upon its mass. More massive black holes have larger radii. A black hole with the mass of a sun, our sun, has a Schwarzschild radius of about 3 kilometers, only a little smaller than the radius of a neutron star of the same mass. But a black hole with 10 times the mass of the sun has a Schwarzschild radius of about 30 kilometers. So, what lies within a black hole? Well, we cannot answer this question observationally or even in principle, but no information, as we so far know, can emerge from within the event horizon, although we do have theories of evaporating black holes. Nevertheless, we can use our understanding of the laws of physics to predict what should occur inside a black hole. Because nothing can stop the crush of gravity in a black hole, all the matter that forms a black hole should ultimately be crushed into an infinitely tiny and dense point at the black hole's center. We call this point a singularity. So the entire mass of the star is now crushed into the point known as a singularity, smaller than even the head of a nail. We can now see that the structure of a black hole is quite simple. As shown in the figure, it has only 2 main parts: a singularity at the center, surrounded by a spherical event horizon. Note that while a black hole's effects on space and time away from the singularity are fairly well understood, the singularity itself, with nearly infinite density, poses both mathematical and conceptual problems in physics. So, as might be apparent, we don't know a ton about these objects quite yet, but we're working every day to find out. A black hole's outward appearance tells us nothing about what fell in. Any information about the objects that collapsed to make the black hole is lost. For example, if we found an isolated black hole floating through space, we'd have no way to know whether it was made from the collapse of an iron core of a massive dying star, or from the merger of, say, 2 neutron stars, or 2 black holes, or so on. The black hole similarly destroys nearly all information about matter that falls into it at later times. Tossing a 1 kilogram block of lead into a black hole would have precisely the same effect as tossing a 1 kilogram mass of diamonds into it. In both cases, the black hole's mass would increase by a kilogram, and there would be no other evidence left to tell what went in. In this sense, a black hole would appear to be what we would call an information sink. In general, despite being an information sink, we can still measure 3 properties of black holes. First, we can measure the mass of a black hole. One way to do this would be by placing satellites into orbit around the black hole. After measuring the size and period of the satellite's orbits, we can use Newton's form of Kepler's third law to determine the mass of the black hole. The mass is equal to the total mass of all the material that has gone into the black hole. Second, we can also measure the total electric charge possessed by a black hole. Like gravity, the electric force acts over long distances. It is a long-range interaction that is felt in the space around the hole. Appropriate equipment on a space probe passing near the hole could measure the strength of the electric force, and the electric charge could thus be determined. In actuality, we would not expect a black hole to possess much electric charge. For example, if a hole did happen to start off with a sizable positive charge, it would vigorously attract vast numbers of negative charges from electrons in the interstellar medium, which would soon neutralize the hole's charge. For this reason, astronomers usually neglect electric charge when discussing black holes. Third, we can detect the effects of a black hole's rotation, that is, its angular momentum. An object's angular momentum is related to how fast it rotates and how the object's mass is distributed over its volume. Again, think about a figure skater with her arms out, and as she pulls her arms in, she moves more quickly. This same effect explains the rotation of the solar nebula, as well as why neutron stars spin so quickly. We expect black holes that form from a rotating star to be spinning extremely rapidly, but we won't go into rotating black holes too much. Well, there also exists a different kind of black hole. Stellar evolutions make it possible to form black holes with masses several times that of the Sun. But calculations suggest other ways to form black holes that are extremely large. Galaxies formed in the early universe by coalescing gas clouds. During the formation process, some of them will during the formation process, some of a galaxy's gas might plunge straight toward the center of the galaxy, where it collects and compresses together under its own gravity. If this central clump has enough mass, it can actually form a black hole as well. Typical galaxies have masses of about 10 to the 11 solar masses. So even a tiny percentage of a galaxy's gas collected at its center would give rise to a supermassive black hole with a truly stupendous mass, greater than 1,000,000 solar masses. Supermassive black holes are found in the center of almost all currently known galaxies. In 2009, a team of astronomers using the SWIFT spacecraft used the luminosity output of a certain certain black hole to measure the mass of its central black hole. To their surprise, they found out that the central black hole of this galaxy is actually 10,000 times more massive than the black hole at the center of our galaxy, or equivalent to 40 billion solar masses. That makes it one of the most massive black holes or objects discovered in the entire universe. So here's a simulated picture of this object. This object is so large that here, this tiny little ring, I don't even know if you can see the blue, that is our entire solar system. The black hole is significantly larger, roughly 1,582 astronomical units in diameter. In other words, its diameter is 1,582 times the distance of the Earth from the Sun. So these things are incredible. So some people would question, what evidence do we have of black holes? I mean, black holes are black and space is dark, so how do we see them? Well, as one example of the evidence for these black holes, we can actually track and project the motions of stars at the center of even our own galaxy, the Milky Way. From this visualization, we can see that the stars orbit around a point that has huge gravitational pull. Note, this star is just added. There's no actual physical star there, but that's the location of where we believe our galaxy's black hole is. And you can see the paths of actual stars, and this is the date, so this is their year, 2007, 2008, and so on. We can see all these stars are orbiting something. We don't see that something, but they're all orbiting it. So this is our galaxy's supermassive black hole. Now, we're going to get into my favorite part of the lecture. What happens if you fall into a black hole? Now, of course, this is still very much theoretical. Nobody has done it, and it might be an incredibly long time until we even send a probe or anything to do such a thing. But let's get into the hypotheticals a little bit and discuss what can happen. Imagine that you are on board a spacecraft at a safe distance about, let's say the star has about 5 solar masses, or the black hole does. A distance of 1,000 Schwarzschild radius away, or 15,000 kilometers, would suffice to keep you safe. You now release a space probe with a video camera and let it fall into the black hole. So what will you see from the camera as it falls? Initially, at the 1,000 Schwarzschild radius away from the black hole, the video camera would send back a rather normal view of space. But as the probe approaches the black hole, the bending of light by the black hole becomes more pronounced. Light rays passing close to the black hole are deflected so much that the background stars are severely distorted, and you can see that in the bottom of the image. For the black hole in this figure, light from a bright object directly behind the black hole is warped into the feature that we discussed earlier known as a gravitational ring. And in this case, this is from a supercomputer. This image is from a supercomputer simulation. You can see a massively distorted image. That's actually a galaxy that was placed behind the black hole to create this Einstein ring, also known as gravitational lensing. So this is what we see as we fall in. So we see this distortion taking place, but it gets way more interesting. How will the probe itself look from your vantage point on the spacecraft at a safe distance? To discuss changes in the probe, let's assume first that it emits blue light and that it has a clock that was initially synchronized to a clock on the spaceship. So here's our probe, just a blue square with a clock on it. And we have times that match up between it and the clock on our spacecraft. You might expect that as the probe falls, the speed should continue to increase, right? It moves quicker as it falls. This expectation is true, but up to a point. As the probe approaches the event horizon of the black hole, where its gravity is extremely strong, the gravitational slowing of time, or time dilation, is so pronounced that the probe will actually appear to slow down. From your point of view on the spacecraft, the probe will actually take an infinite amount of time to reach the event horizon, where it will appear to remain suspended for all eternity. You can see the slower passage of time by comparing the clocks on the spaceship to the clocks on the probe in the figure. So, first off, an object falling down into a black hole will appear to fall forever. But it gets weirder still. As the probe falls, to watch these effects, we would need special equipment. The reason for this is the gravitational redshift, and hence why we started out saying that the object is blue. As the probe falls, the light reaching you from the probe is shifted to longer and longer wavelengths. The probe's blue light will turn green, then yellow, and then red. And then it will continue along the electromagnetic spectrum and eventually fade into the infrared wavelengths that our unaided eye cannot see. Therefore, while the object appears to never cross the event horizon because it takes forever to fall, any light that it emits anyway will be disappearing from view and it will vanish. So either way, we won't see it. But it still gets weirder. If you could view the falling probe with goggles that tracked light for ever-increasing wavelengths, you would see it come to an unpleasant end. Near the event horizon, the strength of the black hole's gravity increases dramatically as the probe moves even a short distance closer to the black hole. In fact, the side of the probe nearest the black hole will feel a much stronger gravitational pull than the side of the probe that's opposite the black hole. In other words, the front of the probe experiences way more gravitational effect than the back. Well, that's a problem. These tidal forces are like those that the moon exerts on the Earth, but are tremendously stronger. The sides of the probe are actually pulled together by the hole's gravity and makes them fall in straight lines toward the center of the black hole. The net effect is that the probe will actually be stretched out along a line pointing toward the hole and squeezed together in perpendicular directions. This stretching is actually called, and this is real, spaghettification. This effect is so great that it will rip even the strongest materials apart into just a series of atoms. So, for an amazing look at what happens in more detail, I really recommend watching the video by Crash Course Astronomy, linked in the description. They talk about everything we discussed so far in some more detail, and they also give you an idea of what it might look like if you fell into the black hole looking backward at the universe. It's pretty remarkable, so I would recommend watching that here. And before I end this video, I just want to mention that neutron stars and black holes are some of the craziest objects in the universe. There's so much to discuss when talking about them, I can't even compact it into this one video. But for the sense of my course, I want to keep this lecture sort of brief, and so we'll leave it here. So if you are really amazed by these things, I highly recommend going out and doing your own research or finding a book on the subject to read and really explore these ideas, because they are mind-blowing. So if you love this as much as I love sharing it, I encourage you to look into it more. So this is my first upload in over a year. My goal is to upload another video or two, maybe a couple, on galaxies and on cosmology, perhaps, and maybe even extraterrestrial life and planets. So that's going to be coming down the road a lot. I have other courses to teach in the meantime. But for now, thanks for watching and have a great day.